Welcome back to ME 760 Engineering Analysis 1. So last time we concluded the chapter 4 first order differential equation, and today we will start the new topic about solving the higher order differential equation, especially the equation with constant coefficients and also variable coefficient. But we will start today the definition about the higher order differential equation with constant coefficients. This chapter again is not included in the book, so I uploaded the two chapters for the higher order differential equation. The one I think solving the higher order differential equations, and the other one is the series solution for differential equation, both as one PDF file. I uploaded to the hands-out, I think, folder in the K-State Online. So let's start. So higher order ODEs. So usually we have yn is the nth differential of y, so this is just dny by dx to n. So the general nth order ODE usually will have the form dny by dx n equal to some function of x, y, y1, y2, up to yn minus 1. So let's call this equation number 1. If you remember, when we define the general formula or general form for nth order differential equation, this was dny by dxn plus an minus 1 dn minus 1 y by dx n minus 1 plus an minus 2 up to a naught y equal to some function g of x, and this was the general formula. But you can also write it as dny by dxn equal to some function of f of x. Here x will be the g of x and also the coefficients, if the coefficients are a function of x. So you have a function of x, function of y, y1, y2 up to yn. So if we let the differential here d by dx as d, and d just is an operator. If you operate over the dependent variable y, will give you dy by dx. So this is just a differential operator here. We can write the general formula or general form for the differential equation to be dn plus an minus 1 multiplied by dn minus 1 plus an minus 2 multiplied by dn minus 2 plus up to a naught y. So this would be a naught all operated over y will be equal to g of x. So this is just, we rewrote the general form of the higher nth order differential equation to be just an operator equation. So this is called operator equation. So dn means the nth differentiation, the nth differential for the function y of x, and dn minus 1 is dny by dx n minus 1, and so on. Why we are writing this like in this format? Because this is now a polynomial of degree n for the operator d. So this is just polynomial of degree n for D. So we can solve this polynomial equation, and it will give us D minus lambda 1 multiplied by D minus lambda 2 multiplied by D minus lambda 3, and so on up to D minus lambda n equal to multiplied by y equal to g of x. So this is just a polynomial equation that you can decompose it to the n roots for this polynomial of degree n, and each one of those roots is lambda 1, lambda 2, lambda 3 up to lambda n. So lambda i's are the roots of the polynomial, are roots of the polynomial. And we can write the polynomial again as lambda n plus a minus 1 lambda n minus 2 plus a n minus 3 minus 2, sorry, lambda n minus 2 up to a n equal to 0. So if you just replace these here with the symbol lambda, so this is a polynomial of degree n of lambda. Solve it, get the n roots of this polynomial. So the n roots of those polynomial will be lambda 1, lambda 2, lambda 3, lambda 4, and so on. So from the theory of polynomial, we knew that if ai are real, so if the coefficients of the polynomials are real, you might get real or complex conjugate solution for lambdas. So lambda i's are either real or complex conjugates, complex conjugate pairs. So they are either real or complex conjugate pairs, and in order to show this, let's assume that we have lambda minus alpha 1 is one of the roots. We will solve now this polynomial now. So we have lambda minus alpha 1 multiplied by lambda minus alpha 2 multiplied by, let's assume that we have lambda alpha 1, alpha 2 are two distinct real value roots, and we have also a complex conjugate pair. And let's assume that the complex conjugate pair is lambda minus alpha 3 plus I beta 3, and this is the first of the pairs, minus lambda minus alpha 3 minus I beta 3. So let's assume that we have a third order polynomial, and we have three roots, 1, 2, and this is a complex pair, four roots, for example. So if you multiply those 1, 2, 3, 4 brackets by each other, you will get lambda 2 minus alpha 1 plus alpha 2 multiplied by lambda plus alpha 1 alpha 2, and this will be multiplied by lambda square minus lambda to alpha 3 plus beta square 3. So you will notice that you will end up with a polynomial with real coefficients. Okay, guys, so this is just to show you that if you have a polynomial of real coefficient, you might get a real roots or complex conjugate pairs of your roots. So this is just to show that, okay, if you have an alpha 1 and alpha 2 and those are real, and then you have two complex conjugate, alpha 3 plus I beta 3 and alpha 3 minus I beta 3, if you just substitute here, this is fourth order polynomial, and you multiply those four brackets by each other, you will obtain those two equations here, and you will notice that alpha 1 and alpha 2 are real, alpha 1 and alpha 2 are real, beta 3 is real, alpha 3 is real. So when you will multiply those two brackets, you will get fourth order polynomial with real coefficient. So if you have a real coefficient for a polynomial, from the theory of polynomial, it states that if you have real polynomial coefficients, you will obtain either real roots or complex conjugate pairs of roots. And this is just a simple derivation for this. So as an important theory for ODE, we will not give the proof for this theory here. We will talk about the general ordinary differential equation with variable coefficient. So P of x will be not constants, are not constant. So this is important theorem for ODEs. So I think we have so let's call that this is 2 here, or let's call it dn y by dxn plus an minus 1 dn minus 1 y by dxn minus 1 plus an minus 2 dn minus 2 by dxn minus 2 for y a naught y equal to g of x. Let's call this 2 instead of this. So let's actually call so it is with variable coefficient instead of just a constant coefficient. It's with variable coefficients. So this is the general form for the ODEs, nth order ODE. It's linear. Why it's linear? I do not have any higher order for any of for the highest order. I do not have any higher degree than what? Than 1. So this is linear differential equation of nth order differential equation, linear with variable coefficients, because your coefficients now are function of what? Function of x. So this is with variable coefficients. So usually the general solution for this equation will be something like y of x will be some constant c1 multiplied by y1 of x plus c2 multiplied by y2 of x plus up to cn yn of x plus some y particular solution as a function of x. So this is usually the general solution for the nth order differential equation. So if you plug your y1 solution here in the general form of the nth order differential equation, what you will obtain? y1 or y2 or up to yn. What you will obtain? 0. Yes. So those are the homogeneous solution, homogeneous equation solutions. And they are what? How many of those? N. So if I have an nth order differential equation, I should have what? N solutions. Okay? So those N solutions will be the solutions for the nth order linear differential equation with variable coefficient or with constant coefficient. In both cases, it does not matter. You will have nth solution. If you substitute with any of those solutions, it should satisfy the homogeneous equation. And the homogeneous equation is what? This plus this plus this plus this plus this equal to 0. Then you will have another solution, which is the y. Sometimes they call it particular integral. Particular integral. So pi. Sometimes they call it y pi. Sometimes they call it y p. So sometimes they call it y particular solution, or in the book, I think the chapter I uploaded online, they call it y particular integral. So do you understand? If you substitute with the particular integral here, what you will get? Instead of getting 0, you will get what? G of x. Okay? So if you substitute with this solution here, you will get what? You will get for this part 0, and you will get G of what? Of x. So again, from the matrices and linear vector spaces, we said that if you have the eigenvectors for the matrix, yes, and you have those let's say you have distinct eigenvalues, lambda 1, lambda 2, lambda 3, lambda 4, and so on. Let's say we have 3 by 3 matrix. How many eigenvalues? 3 eigenvalues. We stated that if you have distinct eigenvalues, you can represent corresponding eigenvectors as what? As a basis for the vector space. And what do we mean by a basis for a vector space? That those 3 eigenvectors are linearly independent. So they are linearly independent. So again, if I have an nth order differential equation, I will have what? N solution for the homogeneous equation. And if those nth solution for the homogeneous equation are linearly independent, any combination of those solution will be also a solution for the differential equation. This is what we said also in the matrices. We said that if you have V1, V2, V3, any combination of V1, V2, V3, like C1, V1 plus C2, V2 plus C3, V3, will be also a solution for what? For the matrix. So this is again, any combination will be also what? A solution. So this is the general solution. Now, how we will get the CIs? So where those CIs here are arbitrary constants, and the yi of x are independent solutions of the corresponding what? What equation? Homogeneous equation. And yp is what? Yp is solution of the inhomogeneous equation, meaning g of x does not equal to what? Equal to 0. So, and it is y of b is any solution that will satisfy that satisfies equation number 2 over there, this, that satisfies 2 but not necessarily the initial or boundary conditions. So this entails that there is no singular solution. Now, how we will calculate the CIs, those coefficients here? If you have a solution, a general solution like this, how we will obtain C1, C2, C3, and so on, Cn? Yes, initial condition, and what else? And boundary condition. So usually, typically, if you have y at x equals 0 equal to some constant, let's say k0, and y prime at x0 also is equal to some k1, and y double prime at x0 equal to k2, and so on up to y n minus 1 at x0 equal to kn minus 1. Those are called initial what? Conditions, because you are defining the function x, y at initial value x0, you are defining y prime at x0, y double prime at x0, up to yn minus 1 at x0. So this is, you are giving initial values for all the independent variables and their differentials. So y prime, y double prime, up to yn minus 1. So what about the boundary values now, or boundary conditions? So I will define y at x what? x1 equal to k1, and then I will define the same function y at what? x2, and this will be what? k2, and I will define y at x what? xn minus 1, for example, and this will be what? kn minus 1. So I only define what? I only define my function y at what? So let's say that this is the domain, this is the boundaries, so I will define y here at x1 here in this location, and y at x2 here in this location, then y at x3 in this location, and so on. I did not define the derivative of the function y. I just define the function y at different boundaries. What's the value at different boundaries? So this is called what? Boundary conditions. Or you can get a mix of what? Initial condition and boundary condition. So this is, let's say that this is A, and this is B, and this is C, or you have a mix of initial condition and boundary conditions. So under what conditions are those solutions y1, y2, y3, and yn of the homogeneous equation are linearly independent. Do you remember what's the condition for linear independence? When we have for matrices, what's the condition for linear independence? If we have V1, V2, V3. No, but instead of just defining it by matrices, we define what?
The rank.
Not rank, no. I'm talking about the formula that I give. C1, V1 plus C2, V2 plus C3, V3 is equal to 0 for only C1, C2, C3 equal to 0. Do you remember this? Yes? So this would be exactly the same here. So the condition, so we have to say the set of solutions are yi of x's are linearly independent under the following condition: f k1 y1 of x plus k2 y2 of x plus k3 y3 of x plus kn yn of x equal to 0, and let's call this number 4, implies that all ki's are zeros. So if you want those to be linearly independent, you will not find any linear combination for y1, y2, y3 up to yn except with coefficient equal to what? 0. Okay, guys? So I cannot get, excuse me, I cannot get, for example, 2y1 plus 3y5, y2 plus 5y3 and so on equal to 0, and this will not happen. So the coefficient should be equal to 0 for this to be satisfied, and in this case y1, y2, y3 will be linearly independent. So what does it mean if they are linearly independent?
You can't make one by one from combination.
Yes, exactly. I cannot say that y1 equal to negative k2 y2 negative k3 y3 negative kn yn divided by k1. I cannot make it. So it's not, one of them is not a linear combination of the rest. Did you understand? So let's try to see, to solve this equation number 4 for ki's. If we want to get k1, k2, k3, what's the condition for those k's so that this will be a linearly independent solutions. So if we differentiate number 4 once, so this will give us what? K1 y1 of x plus k2 y21 of x plus k3 y3 prime of x plus kn yn prime of x equal to 0. Differentiate it second time, so this will give you what? K1 y1 double prime of x plus k2 y2 double prime of x plus k3 y3 double prime of x plus kn yn double prime of x equal to 0, and do this until the nth minus 1 derivative. So this will be what? k1 y1 n minus 1 of x plus k2 y2 n minus 1 of x plus k3 y3 n minus 1 of x up to kn yn n minus 1 derivative of x equal to 0. So I can rewrite those nth equations. So how many equations here? Yn. You have 1, 2, 3, let's say n is 4, so you have 3 equations only. So n minus 1 equations, and this will make them what? N equations. Yes? So let's assume that n, you are interested in the 4, n equal to 4. Okay, derivative. So you will have first derivative, second derivative, what? Third derivative, and then you will have this equation, you will have 4 equations. So now we can write these equations as in matrix form, and this would be k1, k2, up to kn, and I will put here y1 of x, y2, y3, up to what? Yn. Then I will put y1 prime, y2 prime, y3 prime, yn prime. So here I will put what? N minus 1 prime. This will be what? Yeah. 1. y2, n minus 1, up to what? N minus 1. And this is equal to what? 0. So we knew from solving set of equation, algebraic equation using matrices, that you have a matrix A multiplied by a vector K, and this is homogeneous equation. So you have only how many solutions? Either you have a solution or no solution. Yes, trivial solution. Yes, so you have a trivial solution, or which is 0, or a solution, but this solution will be an infinitely many solution depending on each other. Yes, so in order to have the trivial solution, what will be the trivial solution? This determinant should not be equal to 0. So if determinants, let's say this is A, so if the determinants of A does not equal to 0, so I will have what? The vector K will be equal to what? 0, and this is what? Trivial what? The trivial solution. If the determinants of A is equal to 0, if the determinants of A is equal to what? 0, this means that this vector K will not equal to what? Not equal to 0. But we are seeking the condition of when K1, K2, K3, K4, and Kn are equal to 0, so that we will have linearly independent solution. So what will be the condition for the linearly independent solution? The determinant of A is not what? Is not 0. So that this will be what? 0. So if this is 0, we have a linear independent solution from here. We said if you want to have linearly independent solution, y1, y2, y3, y4, this is the condition for the linear independence. And this will not be satisfied unless k1, k2, k3, k4, up to kn are equal to what? 0. So from here, if you want your k vector equal to 0, you have to have the determinant. This determinant is what? Does not equal to what? To to 0. And this determinant here is called W of y1 up to yn, and it is called Wronskian. Again, so this is the Wronskian, and this is the determinant of what you see here, y1 up to y1 n minus 1, y2 n minus 1, and yn n minus 1. Do you have any questions so far? So this is just if we have an nth order linear differential equation with variable coefficients. Again, you will have two solutions. One is called the homogeneous solution, which is y1, y2, y3, and so on. And usually, some of the books will call this homogeneous solution. So y1, y2, y3, and yn. So those yi of x, this set of yi's, usually some of the books will call it complementary function. I do not know if you will find it in this book or not. And yp is what? Particular integral. Particular integral. So your solution will be what? Y complementary function plus y particular integral. Okay, guys? So now, let's go ahead and look for how to solve the nth order differential equation with constant coefficient now. So this will be the topic of this lecture and maybe the next lecture also. So solving linear nth order differential equation, ODE, with constant coefficient. So instead of writing every time dn by dxn of y plus dn minus 1 by dxn minus 1 and so on, we will write this as a linear operator L operated over y, and this is dny by dxn plus an minus 1 dn minus 1y by dxn minus 1 plus an minus 2 dn minus 2y by dxn minus 2 plus a naught y equal to g of x. So can somebody tell me what's the difference between this one and the one with variable coefficients? Huh?
Or all of your coefficients are not functions of x.
So I wrote here a to mean what? Constant. But when it is a variable, I wrote as what? P of x. P of x can be any function of x. Okay, guys? So how we will solve it? So usually we'll start by solving what? As I stated here, the complementary function, which is the solution of what? Homogeneous what? Homogeneous equation. And this is the what? Inhomogeneous what? Equation. So we'll start by solving the solution for homogeneous equation. So again, you remember when we wrote this as the operator D equation in operator D. It was like a what? Polynomial. Yes? dn plus an minus 1, dn minus 1 plus an minus 2, dn minus 2 up to a naught, all operated over y equal to 0 for the homogeneous equation. Yes? So when we will solve the equation, we got lambdas, lambda 1, lambda 2, lambda 3, lambda 4, and lambda n. Yes? It's easy to assume that, okay, we will say that the solution for this equation will be some exponential function. And if we want to make sure that indeed the exponential function is the solution for this equation, what should we do? If you have an equation and I'm telling you, please check if this solution satisfies this equation or not, what you will do? Plug it in and see if the right hand side will equal to the left hand side or not. So we will assume that our solution for this equation, we will look for a solution in the form of exponential functions e to the power of lambda x. Okay? And we will have yi, which is the ith derivative of this solution, will be just lambda I e to the power of what? Lambda x. So you knew that the exponential function, if you differentiate it, will give you the same function but multiplied by what? By lambda. If you differentiate it twice, you will get lambda squared, 3 times lambda cube, and so on. So if you differentiate it ith time, it will give you lambda to the power of what? I e to the power of lambda x. So this is the ith derivative of our solution, will give us lambda to the power of I e to the power of lambda x. Just I want to show you this. Why I'm showing you this? Because we have to differentiate our solution in time and then n minus 1 time and so on. Okay guys? So if you do this and you substitute here in this equation, what you will get? So this will give you lambda what? Lambda n e to the power of what? Lambda x plus a n minus 1 multiplied by what? Lambda n minus 1 multiplied by what? This, and this will give me a n minus what? 2 multiplied by what? N minus what? 2 e to the power of what? Lambda x up to a naught multiplied by what? Lambda x equal to 0. So lambda x will go with lambda x, will go with lambda x, will go with lambda x, and you have what? So we have the same. You remember when we just look at the differential operator D, it was dn plus an minus 1, dn minus 1 plus an minus 2, dn minus 2, and so on until a naught equal to 0. And I said we want to seek a solution for a polynomial of degree n like this. Yes guys? So all what we will do now, we want to look for the values for what? For lambda what? Lambdas, lambda 1, lambda 2, lambda 3, up to lambda n. So there is two situations. The first one, if you will have for lambdas, if your coefficients AI again are real coefficients, we will have lambda i's as what? The roots are what? Are either, I just stated this a couple of minutes ago, either real or complex conjugate pairs. I just showed to you when we have a fourth order polynomial and we have alpha 1, alpha 2, and alpha 3 plus I beta 1 or I beta and alpha 3 minus I beta, and we showed that if you multiply those four roots you will get the fourth order polynomial with a real coefficient. So if your AI's are real coefficients, what do we mean by real coefficients? A number, there is no imaginary component. So if you have AI's as real coefficients, your roots for the solution for this equation will be just either real or what? Complex conjugate. So we will look for the case, the first case will be the case of distinct roots and how we will solve it. So we have two situations. The first one you will have distinct roots, and the second one you will have what? Repeated roots. You sometimes, if you have something like this, y minus 1, y minus 1, this will give you what? Y square minus 2y plus equal to 0. So this is lambda square minus 2 lambda plus 1 equal to 0. You will have y lambda equal to what? 1 and lambda equal to what? 1. Those are not, they are the same roots, so they are not distinct roots. Yes, in this case we will have a little bit different way to tackle the problem, because if you have lambda equal to 1 and lambda equal to 1, you will notice that you knew that our solution was what? C1y1 plus C2y2 plus C3y3 up to Cn plus the particular integral. In this case, y1 and y2 will not be linearly independent, so we have to look for something else. But for right now, I will show you the case where we have distinct solution, and we will continue this next time. And also I will show you the case where we have similar roots or repeated roots. So just in a minute, I will. Actually, it is. I have only 2 minutes, so it's better not to start and continue next time. So next time again, guys, I will show you if you have a distinct roots, what we will get, and if we have a multiple roots, what we will get. So do you have any question for this today's lecture? Nothing? Okay, guys, have a good day.